Hello, it's Keith here, and this is lesson 3 of my TMS9900 assembly programming tutorials. Now, we looked last time to addressing modes. We've looked at a few basics in the past. We're going to carry on today. We're going to be looking at byte commands that work at the byte level rather than the 16-bit word level. And also we're going to be looking at branches, conditions, jumps, things like that. So we're going to be sort of delving in a little bit further into the kind of things you're going to need to be able to do some programming on this processor. So let's go straight over to the code and let's see things in action today. Okay, so as I say, this is a combined lesson covering the byte commands and also the conditions. So as usual, we've got some jumps here and we're going to be jumping to different sections to run our code. Of course, you can get the code from my website along with the build scripts that I use to run things today. Let's go and fire it up and see what happens. Okay, so here's my emulator starting up. I just press a 2 here and then 2 again to select the cartridge. And here we go. Here's the example running. So let's jam this to the top here and let's see what's actually happened. So first of all, we're showing an area of memory here, and this is the test data which we've got just here, and you can see that has been transferred to the RAM and it's being shown on the screen just here. So we're going to be using this in a variety of tests. We're loading the address of that test data into R0 here, and then we're using that as the source because of this star specifies use the address in the register as a source. And we're moving a word, as we have done in the past, 16 bits, into R1. And you can see here, R1 has become 1122 just here. And you can see that that is the value just here. So we are able to load in the test data as a word into R1 1122. Now, if we add a B to the end of the move command, move B here, you can see we are doing the same again, but this time we're loading into R2. Now, because we specified a B, we're working at the byte level, and different to every other processor on the planet ever pretty much, the TMS9900 uses the top byte of a pair to represent the byte commands rather than the bottom byte, which everything else would, including the 68000, which is also a big endian system. I don't know why it does that, but it does. Fair enough, that's what it does, so that's what we work with. So yeah, this is the result of the byte command, move B, moving in from R0, moving the value 11 here, into the R2 register here. So the bottom part has been left unchanged, the top part has been read in from this test data here. Now R3, we did the same again, but R3 contained a previous value of FFFF here, and that was to make a point. You see, with R2 we just had zeros there, but if we load in other data, whatever that is, the top byte will be changed because of the move B command. The bottom byte is left unchanged, it's not zeroed. So if you need it to be zeroed, you're going to have to deal with that. That's the point that that example was making. So we've got a move B command. We also have an add byte command, SAB, and a subtract byte command, SB. And you can see we're doing some tests here. We're adding R0, which we've set to 1. In the top byte of the pair, you see the pair is just here, so we need to use that top byte again. There's no load immediate byte command either, so we've had to load a 16-bit pair in here and just using the top byte here. And so you can see here we've done an add byte here, and we've added a byte to various values. R1 we've added to FF, and that's rolled over to 0. R2 was 11, and we've added 1, so it's become 12. And R3 has also become 12 here. And in all of these cases, the bottom byte is unaffected, and that's quite important. Then what we're doing here is we're doing a subtract byte, and you can see we've gone from 00 back to FF here, from 12 back to 11 here, and from 12 back to 11 here. And again, in all cases, the bottom byte is unaffected. As I say, you've got an add byte command, a subtract byte command. You don't have a load immediate byte command. You've got a very limited set of byte-based commands. So yeah, please check out the cheat sheet and see which commands are available, because the vast majority aren't. So in a lot of cases, you're going to have to work with 16-bit values, as I say, like this load immediate, where I'd like to load immediate byte command, but there isn't such a thing. So we just have to work within that. What we do have, however, is a swap byte command. So as I say, when we're loading a byte, we're loading into the top half. But if we need that to be in the bottom half, then we can do that with a swap. You can see here, this 60 has moved to here, and this A2 has moved to here. So the two parts have been swapped around using no other registers, of course. FF had no effect, both parts were the same. This one, 11 has moved to here, and 00 has moved to here, and this one, 11's moved to here, and FF's moved to here. So we can use these swap byte commands to move things around for the times where we're needing to read in a byte and then convert that to a word or something like that. So that's a command that's very handy for us to have. It helps us work with this odd concept of using the top byte as the in the pair as the byte commands, which I say, at least it was odd to me. Maybe if you're more familiar with it, that seems the natural way to you. Me coming from the Z80, it seemed a little odd. Okay, so we're going to be doing some branch tests now. So we're starting off with some very simple branching options here. Now, one important thing to point out is on the TMS9900, unlike some other systems, the jump command is actually a relative jump, so it's working on a +127 to -128 range from the current byte position in code, whereas the branch command whereas the branch command works absolutely and so can jump to very long distances. So you can see here I'm using jump to byte test here because it's nearby, jump to branch test because it's pretty nearby, but then these ones I'm using branch commands because these are having to jump much further in my code. For example, if I just unrem this but I change it to a jump and I just remove this @ symbol here and I compile this, I've now got an error, and the error, it's right at the bottom here, you can't see it, but it says jump distance too big. That jump command can't work at that distance, so we have to change to a branch command with an @ symbol, and then we can compile just fine. We're going to of course see this example later on. I'm just making the point that the jump and the branches are opposite compared to what you might be used to on other systems again. Okay, anyway, we're going to be doing this branching test first, and we're going to just be doing some examples of the branch and link command. So if I just stick this to the top, press 2 and 2 again to start up my cartridge here. Okay, so what's happened? Well, we're using branch and link here, and we're specifying the @ for the address print char, which is a function we're not going to look at today. It just prints a character to the screen. That's really all you need to know about it. So it prints the top character of a pair. So again, we're loading a 16-bit pair, but it's a byte-based command, so it uses the top half, the A here. So we printed an A to the screen here. And then what we're doing now is we are loading R1 with the address of branch test skip here. And then we are branching to the address in, that's what the star means, R1. And so we're effectively skipping this part here, which is why you can see the next letter is the B and not this number 1 here, because this branch jumped over the 1 here. Next, what we're doing here is we're doing the branch in a different way. In this case, we used a register, but here we're using a direct address. So we're using the address at branch test skip here, and we're skipping over this printing of the character number 2 here. You can see all of these are getting skipped over. And so the next character we're showing is the C here. Now what we're doing is a branch and link to the address BL test 1 here. Now BL test 1 here, you can see, is loading the immediate value ! And then it's branching to the address in register R11. Well, what sets the register R11? Well, it's actually the branch and link command. The branch and link command will effectively put, I've written it just here, the return address in R11. So branch to our address in R11 here is effectively a return command. I know it looks odd, but that's what it is, because the address R11 is the address of the next command we should be running. So branching to that is a return. Now, in that case, we're using R11, which is what the branch and link command sets the return address to here. But if we need to use that, for example, for nesting, then we can actually do things differently. Here, branch and link test 2 here is moving register 11 into register 10, doing some other stuff, completely irrelevant stuff, but it's doing some stuff with register 11 here. And then the return command this time is branching to the address in R10, because that is now the address in R11. And we would actually need to do this anytime we've got a branch and link within a branch and link subroutine. So this is using register 11 as well here. I can just prove that to you if I change this to R0 here, and I just take this out and I put this as R11 here. If I just run this, well, we've done our branch and link test 2 here, but you can see the E hasn't been shown, and the reason for that is we've actually crashed because the print char routine, the branch and link, changed R11, so when it returned, it's actually now not returning to the right address anymore. But if we change this back, moving R11 into R10, and then we branch to R10, that will work just fine. And our character E is back now, because our return address being moved to R10, because printchar doesn't use R10, was preserved just fine. Now, the alternative to this is to use workspaces. We're going to look at that later on. This would be where the subroutine uses a totally separate set of workspaces, including the R11 register, so nothing gets damaged. Anyway, that's the concept of branching, and also branching and linking. Branching is basically like your goto or your jump, and branching linking is like your go sub, your call, or your jump to subroutine, pretty much speaking. Anyway, as I say though, the point here is that these branches are occurring. If we just take out this branch here and we take out this branch here, well, now you'll see when we run, we've got a 1 and a 2 being shown because we were no longer skipping over those sections there. Okay, so that's the concept of sort of simple branches that always occur. Now let's have a look at some conditional ones. Now, as I said before, the strange thing about this system for me is that the jump commands are relative and the branch commands are absolute. So this time we're going to be using some conditional jumps, but rather than BEQ and BNE, which would be what I'd be used to, we don't get that. We get JEQ and JNE, but the EQ and the NE mean the same thing. EQ means equals, NE means not equals, and like with most processors, when we do a comparison between two registers, if the difference is 0, if they're equal, then the 0 flag is set. So jump equals means jump if the difference is 0. So we're loading a bunch of tests here, and we're going to be doing some jumping here. You can see we're either going to show an exclamation mark equals or just an equals, depending on which one of these jumps occurs. So it's an easy way of seeing which actually occurred here. Let's fire it up. Now, the idea of all of this is that you should download my examples and not just watch this video. Download the examples and try changing some of these values and some of these conditions and just see what happens. Now, what's happened in this first case? Well, we're comparing R0 to R1 here. R0 equals 10FF and R1 equals 10FE here. Now, we're doing a comparison at the byte level. So we're just comparing this 10 part here to this 10 part here, which of course is the same. The 0 flag that's shown just here has been set. So the jump equals has occurred, and we've just shown the equal sign. Now, that was a CB, compare bytes. If I take that out and just do a compare, well, now we are testing, and it's this comparison command here that's setting the flags, and now 10FF is not the same as 10FE because we're now comparing at the 16-bit level. So we've branched to this with this jump not equals, and the exclamation mark equals has been shown. So that's the comparison command. We can also do a comparison immediate here. Now we're going to use this one. So we're comparing R0 to 10FE. Well, R0 doesn't equal 10FE. So when we run this, of course, well, you can see 10FF does not equal 10FE. So we've got not equals here. But of course, if we change this to R1 and we run again, well, now you can see, of course, the 0 flag is set because we've compared 10FE here to 10FE here. Now, there's no compare immediate byte command, but if you know what the bottom byte's going to be, if you've zeroed the bottom byte, then of course you could use a compare immediate. And if you were doing a greater than or less than, you could do that as well anyway without necessarily clearing that bottom byte. But we've got these commands to work with bytes, the command to work with registers at the word level, and an immediate command, all of which can be used to do a comparison between two values. And in this case, we were jumping if the two values were the same or not the same. Now, as with most processors, we've got a wide variety of comparisons, and like most processors, we need to decide whether the register contains a value that is signed or unsigned. I'm kind of assuming you're going to have done some assembly before when you're looking at this. This is quite a obscure system to learn, but I'm sure there's some people who are TI-99 fans who this is the only one they watch, which is great. But I will explain. The concept of a register, if you think of it as unsigned, goes from 0 to 65535 if it's 16-bit. However, if it's signed, it goes from minus 32768 to plus 32767. Well, how does the processor know whether the register is signed or unsigned? Well, it doesn't. All that matters is the way you use it. You see, -1 in hexadecimal is FFFF, all the bits set to 1. And if you add that value to a number like the number 10, it will roll around to 1 before where it started, to 9. So there is really no definite difference between 65535 and -1 from the processor's point of view. If you add them to a number, the result's going to go down. So the way we have to work with signed numbers with comparisons is we need to use different commands for signed numbers and unsigned numbers so that the processor decides whether that FFFF is 65535 or -1, because they are the same number in the register of the processor. It's just the way they're treated by the software itself. Okay, so we're going to do some comparisons of unsigned numbers first. So we're loading some test values in here, and we're using these branches here: jump higher, jump lower, jump higher or equals, or jump lower than equals. Okay, so we're going to try these two first here, and we've got some test values. And as I said before, you should download today's example, and you should try changing the test values and all the comparisons. First, we're going to compare R1 to R0, and we're going to see if R1 is greater than R0, which of course it is. So one would expect we're going to jump here and show the greater than symbol. What a surprise, we did. R1 was greater than R0, and that caused the jump to over here. Now, we could also do a comparison of some other values. For example, if we compared R1 to R2, well, R1 is less than R2. And so you can see here, we've done the jump if lower, and we've ended up here. Now, as well as higher and lower, we've got higher or equals, or lower or equals. And so in this case, this will work exactly the same. If I just run this. So in this case, of course, R1 is still lower than R2. So that has happened, and we've jumped to the lower. But if I change it so we compare R1 to itself, well, now the result is going to be equals. So in this example, the higher than equals is first in the comparisons. So we will actually show the higher symbol here. I don't have a higher than equals example showing here. But as I say, you can see here that in this case, because the two values compared had a result of 0, the first of these was the higher than equals, so that ran first. If we put this one above in the example here, it would be the one that took the chain of execution, and we would show the lower than symbol. You can see the 0 flag is set there. So these work just fine with unsigned numbers. You can see we can do tests all the way up to sort of 8,000, 9,000, which would be a problem if we were working with signed numbers. You can see these work just fine. In this case, we've compared R2 to R3, 8,000 to 9,000, and 8,000 is less than 9,000, so we've shown the less than symbol. But this would cause a problem if we were working with signed numbers. So let's have a go with some signed numbers, and let's see some similar comparisons with the signed equivalents of those jump commands. So we're loading the same values here, but 8,000 in hexadecimal in a signed number is -32768, and 9,000 as a signed number is -28,672. So this time, when we do some of these comparisons, we're going to get different values. So let's try this one first here. So we're comparing R1, which is hexadecimal 6,000, which is plus 24576, to 7,000 to 8672. I'll just need to run this out, and if we run this, well, this time we're using jump if greater than, and that has of course jumped, and it's jumped to show the greater than symbol here. Jump if less than would branch if the value was lower. So in this case, hexadecimal 7,000 is greater than hexadecimal 6,000, so the jump if greater has occurred. However, if we change and we do this version, we're going to compare R1 to R2. Well, if this was an unsigned number, R1 would be lower than R2, but in this case, R2 is the signed equivalent of -32768. So R1 being below 32767 is plus 28672. So R1 is actually higher as a signed number than R2, even though it would be lower as an unsigned number. And so this is where it becomes important, whether we're using jump if greater than or jump if higher, and jump if lower than or jump if lower. So as I say, in this case, we can use that, and we can see that has worked fine with our signed numbers. Okay, well this time we're going to compare R2 to R1. Now R2 is a negative number, but R1 is positive. So R2 in signed terms is lower than R1. If we just run this, we'll see that. You see, we've done the branch and shown the lower symbol. However, if I use the unsigned versions, this jump if higher and jump if lower here, and I put these in here, now because these are higher up, these will be the ones that take the flow of execution. Well, if we treated these as unsigned numbers, well, because hexadecimal 8000 as an unsigned number is higher than hexadecimal 7000, we've jumped and we've shown the greater than symbol, which is why it's so important we make sure we use the correct symbols depending on if our number is signed or unsigned. So that's why we need to make sure, and that's the options we have available to us on this processor to allow us to deal with signed and unsigned conditions. Now next we're going to have a look at the carry. Now for technical reasons with regards to my testing tools here, I'm using this BLWP, this branch and workspace. Don't worry about that, we'll look at that in a later lesson. But what we're doing here is we're showing the status of all of the flags here, and we're repeatedly incrementing R0. Now R0 is dangerously close to rolling over, and the point I'm making here is that is what happens with the carry. So here you can see that the R0 contains FFFD. We've then done an inc, it's gone to FFE, then it's gone up to FFFF, and then it's rolled over to 0, and the 0 flag's been set, but more importantly in this case, the carry flag has been set. We've then done another inc, and the carry flag has been cleared, and then we've got two jumps here, jump if no carry, or jump on carry, and we'll show a C or an NC. Now in this case there was no carry, you can see the carry was clear at the last point, so we've shown NC here. However, if I just tweak this code slightly and take off this last inc statement and run again, well, in this case you can see because we took away that last inc, the carry was retained, and so the jump on carry occurred, and we showed the C here. Now the carry will be set whenever a register overflows, so things like addition, also some rotation commands. We're going to have a look at all of this later on. For now though, I just wanted to show the branching and how that worked with the carry flag. So you can see those are our options there. That's how we can branch based on the carry flag being set or clear. Now related to carry and signed numbers is the overflow. Now overflow was a bit confusing for me when I got started with assembly, because it wasn't really something I needed actually with ChibiAkumas. So even once I'd finished that game, it wasn't something I really understood. Now overflow is where a signed number has unintentionally changed its sign bit. Now if you add 1 to -1, it will become 0, but that's a perfectly normal expected result. However, the problem occurs where you've got a very, very low negative number and you subtract 1 from it. For example, if you've got -32767 and you subtract 1, you'll go to -32768, perfectly fine. If you subtract 1 again, you will go to -32769, or you would expect to, but that's actually over the limit of a 16-bit number. So what the value would actually be is +32767. Very serious problem, and the same occurs if you add 1 to 32767, and that's where overflow comes in. If you've accidentally changed the sign of your register with the last mathematical command, the overflow flag will be set. The idea being you test that before you use the value, otherwise you might have a problem. So you can see here we're doing that test here. We've got our value here, 7FFD. Now 7FFD is a high positive number, and so we keep adding 1 to it until we get 7FFF, which is +32767, the limit of a signed number. When we add another 1, we get 8000. Now there's a sort of thing that where the top bit is 1 with a 16-bit signed number, the sign is negative where it's 0, which is the case for all of these, it's positive. So this is a very low signed number, -32768. The flag, that the sign has just changed, and the V flag, the overflow flag, has been set. We've got a command, jump no overflow, and we're jumping to show an NV here. We don't have a jump on overflow command, so we're just jumping to show the V if this branch didn't occur. In this case, there was no overflow, because while there was an overflow here, that wasn't the last command we ran. So the last command cleared the overflow because we went from -32767, because we went from -32768 to -32767. Again, if I take off this last inc statement, we'll leave that flag unchanged. I'll just press my 2s here, and you can see the overflow flag was still set here. So we branched and we showed the V here. As I say, it may be something you never need. It depends on whether you use signed numbers in this kind of way. Of course, you're going to have to use signed numbers in the sense of moving objects to the right and the left, but you may never have to keep a unsigned number as a value that you need to think of in that way. You know, you might, if your game only has positive scores, you're not going to have to worry about the score going from a positive to a negative. You might have to worry about that if you do have negative scores. If you had a game that was like a money management game and you had positive or negative money, you know, negative meant you were borrowing it, you wouldn't want to borrow so much you ended up in positive credit again. So yeah, as I say, it just depends on what you're using the code for, but it's a interesting flag. It's a very logical flag once you understand it, but I didn't originally understand it, so I do like to point out its use to try and help people who maybe didn't understand it like I certainly didn't. Okay, so next we're going to look at the parity flag again, another one you may never need, and I think this one really comes down to the sort of the side of things, maybe the more hardware side of things, where you're reading in from tapes, punch cards, things like that, or barcodes as well, of course, maybe. There's going to be times where you need to actually check that the data you're reading in hasn't got corrupted in a simple way, and this is what parity is all about. You may have come across this in some sense. You know, there are cases where you are reading in data that may have become corrupted, and this is a simple way of checking that. The way it works is the parity bit is set when the number of bits that are 1 is odd. So if we look at this first value here, well, this has got a value of 4, which is 100 in binary. So there's 1 bit, and the parity bit has been set because 1 bit set to 1 is an odd number of bits. When we add 1, it becomes 101 in binary. This means there's 2 bits that are 1, and the parity is even. So the parity flag has been cleared. Then we added 1 again. This 1 became a 10, so it's now 110, and again, even parity, so no parity flag. We add 1 again, so it becomes 111. The parity is now odd. There's 3 1 bits, so the P flag has been set, and so on. So a bit odd. That's the way it works, though. And as I say, I believe this is intended for things like reading in from a cassette or some kind of other lossy medium that maybe the data hasn't quite been read in right, and you just need a simple way of checking whether there may be an error or not, and this is the way they've used. And this, because it's being done by the processor, a native, it's not as computationally expensive as a CRC byte or something like that. So anyway, this is what it does. In this case, we've got this jump on odd parity here, and we're going to show an NP. So if I run this, well, in this case, the parity was even, so the parity flag was clear, and so we've shown a P. But again, if I change this and I remove this AB and run again, you can see now the parity flag was set. So the GOP command has branched to here, and we've shown an NP. Now, one important thing to notice is that only byte commands set the parity flag. If I change these to ink statements and I run again, well, this time you're going to see that the parity flag has never been set. So this is a command that only works at the byte level, which is why I'm using these AB commands. I think this is going to be, as I say, this is kind of designed for reading in from medium like tape or maybe punch cards on the server side of things. So I guess they would be planning to read in bytes, and I suppose at the silicon level maybe this was a command that would only work on the byte commands. So that's why, I guess that's why we've got that limitation there. But as I say, this is a command I think you're probably never going to honestly need, but it's a command that's there. I think it's very interesting, and I want to discuss all of the commands, so that's what I've done. So there we go. We've gone over quite a lot today, but the understanding of the potential for branching is very important from the point of view of being able to make code that does something, because you're going to need to do things like range checking. I was writing an example today where I'm moving an object around the screen. When you get to the end of the screen, you need to check if you've gone over the edge of the screen to keep the player back onto the screen. So conditions and branching, you got to do them. So you got to learn about them. As I say, please download today's examples and have a go with them yourself. Change the values, change the comparisons, and try and make sure you understand exactly what they do, exactly what the options are, because you're going to need to write your own code that's going to use them later on. Anyway, I hope you've enjoyed this. If you have, please like and subscribe, because YouTube ranks videos by how many people like them. So if you like it, then please let other people find out about it, and they will hopefully enjoy it as well. But whatever you do, I hope you enjoy your programming. I hope you have a lot of success with your programming projects. Thanks for watching today, and goodbye.